and then we're going to move on from the parent function. We're going to spend a lot of time looking at transformations. Okay? Transformations are when we take our parent function that we have here of our quadratic and we move it, or we stretch it, or we compress it, or we flip it. Okay? So all functions have what we call a parent function, and our quadratic is going to be y equals x squared. That's as basic of a quadratic as we can get. So when we graph our basic quadratic function, we can use a table of values, we plot the points, we're always going to get this same exact curve. When we look at transformations, what we're going to do is we are going to move these points relative to what our transformation is describing. Okay? But all the transformations are going to be based on this. Okay? So our basic shape for a quadratic, we call it a parabola. We have our standard parabolas. We also have sideways parabolas. We're not going to be dealing with those, but they do exist. Those are going to be x equals y squared. They're not functions, so I don't want to focus on them right now. I want to stick with the functions. Some key points of the parabola. We start with the lowest point, which is the vertex. Okay? Our lowest point is the vertex. If I end up flipping the parabola, the vertex then becomes the highest point. Okay? The vertex is a good thing to focus on as like a starting point. Okay? When we deal with our quadratics in vertex form, it allows us to focus on the quadratic, on the vertex as a starting point, and then we can graph it and analyze it based on that. Okay? And make changes based on where the vertex ends up moving. The other key feature we have is our axis of symmetry. Okay? So the vertical line that runs through the vertex is the axis of symmetry. Okay? On our parent function, it's the y-axis. That's the vertical line that runs through it. Yeah, the y-axis. But as we move it, as we shift it left or as we shift it right, that axis of symmetry is going to move with the vertex. The important thing about the axis of symmetry is it gives us this mirror image for every point on our line. So if I know some points on the left side of the axis of symmetry, I can use that mirrored property to find additional points and complete the graph. So if I want to find a table of values, I only really need to find 3 points, including the vertex, because then I can mirror the other 2 points. All right? So we got vertex and axis of symmetry. So we've been dealing with standard form. Standard form, if we take standard form and we complete the square, we end up getting a quadratic in vertex form. Ax minus h squared plus k. When we complete the square, we end up getting a quadratic in vertex form, and using that, we can then graph and analyze and manipulate our quadratic based on whatever our needs are. Both forms have different uses. Finding x and y intercepts is really easy with a quadratic function within standard form, but vertex form makes it easier for vertex and tracking transformations. And you'll see that equation again at the end, but we're going to add to it piece by piece. So we start with our basic quadratic. Y equals x squared, or f of x equals x squared. Okay, that's our parent function. It's as simple as we can get. And then what we're going to do is we're going to add something to it. All right, k, just variable. That k corresponds to a vertical shift. Vertical means I'm moving which direction? Not sideways. That's horizontal. Vertical is up and down. So I take my x values, I square them, and then I add or subtract something to it to move it up or down. If it's positive, I'm moving it up. If it's negative, I'm moving it down. Okay? Makes sense, right? Positive goes up, negative goes down. So if we take our parent function, I'm going to graph it real quick. Okay? This is our parent function, y equals x squared. 0 squared is 0, 1 squared is 1, 2 squared is 4. So that's my parent function, y equals x squared. What I'm going to do is I'm going to take y equals x squared and I'm going to add 3 to everything. And so if we do a table of values, you won't need to do a table of values every time, but if we do it, we can see why this change is happening. So if I take negative 2 and I square it, what do I get? Then add 3. If I take negative 1 and square it, 1 and then add 3. 0 squared, add 3. 1 squared, add 3. 2 squared, add 3. So I take all these points and instead of having negative 2, 4, I have negative 2, 7. Instead of having negative 1, 1, I have negative 1, 4. 0, 3, 1, 4, and 2, 7. So I took my parent function and I shifted it, which direction? Up. How far? 3 units. That's what that plus 3 means. I'm going to shift it up 3 units. I'm going to take every single point on that line and I'm going to move it up 3 units. And that's my new function. F of x equals x squared plus 3. Now, based on my new function, that's the parent function. So all quadratics are modeled off of that, and then the transformation is the change. So to get to the point, you don't need that as a reference. You're just going to kind of know what the parent function looks like, and then we're gonna focus on a few things. One being the vertex as our starting point. We're going to track that change, and then we're going to be able to graph from there. Okay. So based on my new graph in blue, my transformed function, what's the new vertex? 0, 3. Anyone remember the domain of our quadratic function? That's all my x values. All of our polynomials will be negative infinity and infinity. Okay? So that one's going to be easy. It's always going to be all real numbers. The range will change depending on our transformation. So the range of my parent function is from 0 to infinity. But now I transformed it. My lowest value isn't at 0 anymore. What's my lowest value now? 3. So when I shift it up, when I do a transformation up, my range also goes up. And that lowest value changes. A couple things I want you to note. That plus 3 gives you the y value of your vertex. That plus 3 gives you the y value. And there was no change left or right. All we did was go up. So the vertex stays at 0 on the x-axis, but goes up 3 values on the y-axis. That 3 also changes that starting point from the range. Okay, so there's some connections there. All right. So we got our vertical shift. Our other kind is the horizontal shift. Notice the difference between the placement of the transformation. What's the difference between those two expressions? Yeah. One is being squared because it's in the parentheses, and one is not being squared. It's being added after the squaring. So that's going to be your major difference between whether it's a vertical shift or a horizontal shift. Good question. Okay? So, add something on the outside, it goes up or down. And this, when we start adding in stretches and compressions, it follows the same pattern. If it's outside of the parentheses, it's a vertical change. You either have a vertical stretch, a vertical compression, or a vertical reflection. If it's on the inside, we have a horizontal reflection, a horizontal shift, or a horizontal stretch or compression. So the inside is a horizontal change, the outside is going to be a vertical change. Now, horizontal shift is special. Horizontal shift is going to be opposite. See how this says plus k and this says minus h? That's your indication that this is going to be opposite of what you think it should be. And so when I have a horizontal shift, if I'm subtracting a number, instead of going left like I want to, I'm actually going to go to the right. When I'm adding a number, instead of going to the right like I want to add, I go to the left. So horizontal change is flipped. So you need to kind of make a mental note of that whenever we're doing transformations. Horizontal shifts are going to be opposite. And we'll demonstrate how that happens with this. Parent function again, okay, just as our reference point, so we can see the change. Okay, parent function. So we're going to take our new one, our transformation, x plus 2, and then we want to square it. So we have to follow our order of operations. So let's start at negative 5. Negative 5 plus 2 gives me what? Negative 3, and then square it. What's negative 3 squared? 9. Negative 4 plus 2, negative 2 squared. Negative 2 plus 2, 0. Squared is still 0. 0 plus 2 squared. And then 1 plus 2 squared. 9. So now I have new points at negative 5, 9. And at negative 4, 4. And negative 2, 0. 0, 4. And 1, 9. So what direction did my graph move? Left, even though it says plus, right? So plus 2 moves it to the left. A minus 2 would move it to the right. And I can look and see this point is 2 units to the left. This point is 2 units to the left. This point is 2 units to the left. So we're shifting 2 units to the left. Where's my new vertex? Now, because we moved left and right, my axis of symmetry also moves. So where's my axis of symmetry at? That negative 2. It's that imaginary line that runs through the middle. Let me change color here. That runs through the vertex. Okay? And when you look at that line, you see how it's a mirror image from one side to the other. Right? Okay? So my axis of symmetry is at negative 2. I want to note, just like with vertex, we write it as an ordered pair to give the location. When we talk about axis of symmetry, it's always written as the equation of a vertical line. X equals negative 2. X equals negative 2 talks about the axis of symmetry. Domain. Always, 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 always. Every single polynomial has that domain. Every single one. Range. Notice there was no change from our parent function's range because we didn't move up or down at all. So the range won't change. Okay? Jody, can you open the door for Gabo, please? I want to highlight something else here. So when we had the plus k, that gave me the y value. The minus h, do a sign switch, gives you the x value. Okay? So notice that comparison. There's a reason we call it vertex form. It gives us information about the vertex. So if we take it and we combine it all into one, now we have 2 transformations. I've got a negative 2 and I've got a plus 1. Okay? So I've got a horizontal change and I've got a vertical change. My horizontal change, I'm going to go which direction? Right 2 units. And then my vertical change, I'm going to go up 1 unit. Okay? So I've got right 2, up 1. So our parent function's vertex starts at 0, 0. If I'm going right 2, up 1, right 2, up 1, now where's my vertex at? 2, 1. And again, we look back at the equation. 2 changes to a positive 2 because it's opposite. Positive 1 stays a positive 1.
Why are you going right to if it's negative?
When I had plus, which way did I go? So if I have minus, which way am I going to go? Inside is opposite. So it gives us the location of our vertex. So you don't need to graph your parent function and move it. You can look at the vertex form and say, okay, I see I have right 2, up 1. That puts me at a vertex at 2, 1. And then what I'm going to do is I'm going to plot 2 more points. So I don't even need the full table of values. Okay? So I know that this is my vertex right here, because I got that by looking at my equation. Pick 2 points on either side of your vertex. Doesn't matter. Okay? Either side. We'll do the left one. If I take 0 and I subtract 2, what do I get? -2. Square it. Add 1. So I have 0, 5. If I take 1 and I subtract 2, what do I get? Square it. Add 1. So I get 2. So I get the point 0, 5 and 1, 2. Okay? Now I know where my vertex is, so that means I also know where my axis of symmetry is. Where's my axis of symmetry? That's where my vertex is, so what's the axis of symmetry? X equals 2. So then if I want to draw my axis of symmetry through the 2, there's my axis of symmetry. I have to be able to get a mirror image for the other side. So referencing my axis of symmetry, if I have a point at 1, 2, what's the mirrored point on the other side of the axis of symmetry? What point on the right side of the axis would be a mirror image to this point 1, 2? 3, 2. What point would be a mirror image to 0, 5? 4, 5. So I don't need to calculate more than 3 points in order to get my quadratic. As long as I have my vertex and then 2 points on one side, I can use the axis of symmetry.
How do you know it's there?
It always runs through the vertex. The lowest point.
I know, but how did you know that 2, 1 was like...
We talked about this is a horizontal shift, right? So the origin, my parent function, y equals x squared, has a vertex at 0, 0. If I'm going right 2 units, then my x value will change from 0 to 2. If I'm going up 1 unit, my y value changes from 0 to 1. So my parent function, the vertex starts here, and then I go right 2 units and up 1 unit, and that's my new vertex. And since that's my new vertex, then my axis of symmetry also moved to follow it, and it runs through the 2. Domain. Always, right? That one's easy. That's like a gimme. That's a freebie question for you. Okay? I had a vertical shift, so that means my range will change. What's my new range? 1 to infinity. 1 to infinity. And again, if you look at the x value of the vertical change, the y value of the vertex, the y value of the range, that was supposed to be try that again. And then again, the horizontal change will give us the vertex x value, which also gives us the axis of symmetry. So a lot of this is tied in together. So we moved 2 units to the right and 1 unit up. Okay, so that's our horizontal and our vertical shifts. So I showed you part of that, or more than this, but we saw part of this earlier. So this is our vertex form where we have a horizontal and a vertical shift. So H gives us the x value of the vertex. K gives us the y value of the vertex. Notice in the formula the negative that's right there. That's why we have that sign switch when we look at the x value. I had x minus 2, gave me a positive 2 for the x value. When I had x plus 2, gave me a negative 2 for the x value. So we're going to have that sign switch. Axis of symmetry is going to follow the vertex. So now what we're going to do is we're going to add in the coefficient. Okay? So the coefficient -2 affects the graph in two ways. One, it makes the parabola narrower. It makes it narrower. We call that a vertical stretch. Vertical stretch. What that does is just makes it narrower. Okay, so we kind of squeeze it in. Pull it, stretch it. Like if you had slime and just stretched it up. Okay, that's what the 2 does. The negative does something different. The negative makes the parabola flip upside down and open in the opposite direction. So our parent function, y equals x squared, is positive. So I have a positive a value. So it opens up. But if I put a negative in front, I have a negative a value, which makes it open down instead. And that's going to have an effect on our range as well. Domain won't ever change, but that's going to have an effect on our range. So we need to be aware of that. Okay? Then I've got one other transformation in here. What's that negative 3 going to do? Down 3. It's going to shift down 3 units. So the negative gives me the reflection. The 2 gives me the stretch. And the negative 3 gives me the downshift. Okay? So now we're adding in a third transformation. So we've got vertical stretch, actually 4 because we've got the reflection. Reflection, vertical stretch, horizontal shift, and vertical shift. We also have horizontal reflections, but I'm not going to cover those. You're welcome. All right. So we talked about its shift. All right. It shifted which direction? It shifted down. How far? 3. Did it shift left or right at all? No. I don't have anything inside parentheses. So the vertex is going to stay at 0 on the x-axis, but it's going to move down. So our parent function starts at 0, 0. We're moving it down 3 units, but we're not moving it at all left or right. So there's my new vertex. I've got my vertex. A parent function real quick. So we can reference that. 0, 0, 1, 1, 2, 4. Okay, there's our parent function. All right. So again, I know where my vertex is, so I know my axis of symmetry. So I just need 2 points on one side. Do we want to do the -2 on the 1 or the 1 and the 2? Sure. -1. Follow our order of operations. So I've got -2 times -1 squared minus 3. What am I going to do first? So what's -1 squared? 1 times 2 minus 3. Okay, 5. Okay. So now I have the point -1, -5. Let's do it with the 2. -2 times -2 squared minus 3. -2 squared. 4 times -2 minus 3. -11. There's -8 minus 3. So I get -11. The -2. Now using the axis of symmetry, I know that I have to have a mirror point at 1 and a mirrored point at 2. So what's going to be the y value at 1? -5. What's going to be the y value at 2? -11. So I use that axis of symmetry as my mirror point. Make that line dotted better. And then there's my new parabola. See how much narrower it is? Okay, so we made it narrower. That was the effect of the 2. That made it narrower. And then the negative is what flipped it and gave us that reflection. So we flipped it upside down and moved it down 3.
What ratio did it make it narrower? And
Not yet, possibly later. by a factor of 2. So it would be, if we wanted to be specific, we would recognize it as a vertical stretch by a factor of 2. Axis of symmetry, 0. There was no shift left or right. Domain. There's your freebie questions. Range. Good. Negative infinity to negative 3. So see how that changes our range, because we always have to start with the lowest number. And since it opens down, that means my lowest value of my range is negative infinity. And now my vertex becomes my maximum instead of my minimum point. And so that's going to adjust how we write the range. Negative infinity up to negative 3. Alright, so this is everything all together. I showed you this at the beginning. Okay, that's our vertex form. We've got A, that's going to be our stretch. It also covers our reflection if we have one. That's the A value. We either have a vertical stretch or a compression. A compression means we make it wider. Reflection is if it's positive or negative. When we're dealing with a stretch or a compression, we're going to look down here at number 3. Okay, the graph is wider than the parent function if the absolute value of A is between 0 and 1. So what that means is if this number in front is a fraction less than 1, disregard whether it's positive or negative. Positive or negative tells me something different. If it's a fraction less than 1, then it makes it wider. If it is a number greater than 1, then it makes it narrower. Okay? If it's a number greater than 1, it makes it narrower. If it's less than 1, it makes it wider. And then we've got our horizontal transformation to give us our vertex. Up and down if k is positive, left and right if h is positive or negative, respectively. Okay? So we're looking at our parent function. And I just want to identify, does it open up or down, and is it narrower or wider? So for the first one, which direction is it going to open, up or down? Why? It's negative. So that says we open down. Now is it narrower or wider? Wider. Because that is less than 1. Okay? Wider. Because 2/3 is less than 1. B. Up or down? Up, because it's positive. Narrower or wider? Wider. 3/4. 3/4 is less than 1. So it's going to be wider. C. Up or down? Down. Same reason as A. It's negative. Is it going to be narrower or wider? Narrower. I don't care about the negative, I care about the 2. Narrower, because 2 is greater than 1. Last one. What way does it open? Opens up. Narrower or wider? Narrower. Because 3 is greater than 1. Down is negative, up is positive, down is negative, up is positive. Oops. Is that an addendum to this? What does that plus 1 do? Moves it. Which direction? Nope. Up. How far? 1. What does this negative 3 do? Down. What does this 2 do? Up. Okay, none of these have parentheses, so there's no horizontal shift. There's no left or right. All of these are outside, so all of these are vertical changes. Alright, so this is the last one. It's already graphed. Okay, so we've got 1/2 x minus 2 squared plus 1. So what does this 1/2 do? It opens up and makes it wider. Makes it winder. makes it wider, and it opens up. Positive opens up, it's a fraction less than 1, makes it wider. Where's my new vertex? 2, 1. Sign switch on the 2, keep the 1. 2, 1. Where's my axis of symmetry? 2, matches with the vertex. What's my domain? Freebie question. What's the range? 1 to infinity. So again, we've got the x value of the vertex, which gives us the axis of symmetry. I'll answer that question in just 1 second. You got the y value of the vertex, and then the change in the range. The reason we changed the sign, because remember our formula is ax minus h squared plus k. It's the minus h. That's why we changed the sign. And if you look, when we plug in the values, if I plug in the values compared to my parent function, it shifts it to the right. The reason is you have to move the x value to the right in order to get back to the same y value as on the parent function. All right, so that's that sign switch. It seems weird. It's counterintuitive. So your best case is just remember it. Inside is opposite. Okay. There are horizontal stretches and compressions. I won't be covering them, but they have the same effect. A number that's larger than 1 does a compression instead of a stretch. Okay, because we're dealing with the inside. Everything inside this grouping behaves opposite of everything outside the grouping. All right, and the thing with our quadratics is this format transfers to every other function. Every other function that we have for transformations models that same exact thing. So if I have my quadratic and I have a compression of 1/2, right 2, up 1, I could make this, instead of a quadratic, I could have a square root function. I can have g of x equals, negative, 1/2 square root of x minus 2 plus 1. And it has the exact same transformations as that. I could have h of x equals 1/2 log of x minus 2 plus 1. Same exact transformations. So it follows through with the rest of our information about functions. So even if you get a function, you ask about the transformations, you don't have to know what the parent function looks like. You just know outside of grouping, vertical stretch or compression. Inside is a horizontal shift, outside is a vertical shift. And it follows through continuously.